Hey everybody, welcome to Heat Transfer. Just doing a quick example here of the relation between the thermal boundary layer and the velocity boundary layer. Usually when you're looking at a plate moving through air or something, and you look at the boundary layers right here, they both follow these curves, but depending which one is on, the one that is on top varies depending on the Prandtl number of the fluid that you're working with, basically. So sometimes thermal will be above, sometimes the velocity boundary layer will be below. If you're looking at how temperature changes from the boundary layer to the surface, it follows this kind of curve. If you're looking at how velocity changes, it follows this kind of variation. So those are just a couple of notes here. In this case, the fluid is at 300 degrees C, and we're working with air, water, oil, and mercury. So I'm going to go ahead and do these sketches here for you of the different boundary layer relations for the different fluids that we use. So for air, I don't know, I was jumping ahead of myself there. The relation between the boundary layers follows the this right here, which is the thickness of the velocity boundary layer over the thickness of the thermal boundary layer is equal to the Prandtl number to some power. In this problem, since the Prandtl number isn't really defined, or well, the power isn't really defined for us, we're just going to go ahead and assume that to be 1, just to make it a little bit easier for us. So we have the Prandtl number, and we need to figure out kind of what the relation is between these two. And since we're just doing sketches, we don't need values for these, we don't have to solve for these. So it's a little bit easier. So for air, PR is equal to 0.71, we're going to say, that's the Prandtl number. For water, you get these values from the book charts, by the way, in your book at temperature equal to 300 C. C equal to 300 K, sorry. PR equal to 5.83. Oil is going to be 6,400. And for mercury, it's going to be 0.0248. Okay, so for air here, we have this plate moving through air, and we have delta over delta T, equal to 0.71 for the one. Okay, so basically all you have to do is to figure out kind of the distancing between these two is what value of delta T over under delta would give like 0.71. So if I drew delta right here, there's no requirement that I have to put it anywhere, so I can sketch it right there. That's about where it is, I would say. So what delta T would give that? Well, it's going to be a delta T that's just a little bit larger. Oh, sorry. I wanted to draw the delta there, not a delta T. So a delta T is just a little bit larger than delta will give it. So I'm going to draw that right about there. So this is going to be delta T. So the distance, delta T, say right here, over this right here, so we can call that delta and delta T, that's basically what it is as a distance, is going to equal 0.71, which makes sense. So it's a pretty easy just little ratio there. You can kind of guess it because all we're doing is sketching here. You don't have to be exact. So then for water, going like this, we've got this, like that. Okay, and let's say I draw a delta right there. You can just draw a delta right off the bat because we're doing sketches. It is equal to delta over delta T is equal to 5.83. Okay, so for this, delta T is going to have to be about 1/5 or 1/6 of delta. So that's going to end up having delta T like down here somewhere. And you can see that between air and water, the delta T has changed the locations with respect to delta, the velocity boundary layer. And this is really dependent upon how easily the water transfers heat through itself, or how well it transfers velocity through itself. So the material properties are very, mess with these a lot. If you had alcohol, maybe these two would switch because alcohol transfers heat a little bit quicker and isn't as thick as water. So, I mean, you can mess with viscosity and everything else because the Prandtl number is, let me go ahead and say PR equal to CP the specific heat coefficient all over the viscosity, kinematic viscosity, all over K, which is its convective coefficient, which also goes to viscosity over diffusivity. So its ability to move heat as compared to its ability to move velocity or move through something. So that's how you can kind of see that relation. And this ratio right here, this is a heat ratio, this is a velocity ratio, this is a velocity ratio, this is a heat ratio. So you can see how that can match up. Okay, so moving on to oil, you've got your bar right here. We'll go ahead and draw delta here someplace. And we got delta over delta T is equal to 6/400. So delta T has to be 1/6400th of delta. So it's going to basically be down here somewhere. So close we can barely even see it. Which makes sense because oil is a very convective material. It takes heat and transfers it really well. So it makes sense that the boundary layer would be used up and get to the point it needs to be very closely. But at the same time, oil is also a very slow and viscous fluid. So the velocity is going to be way farther out than the temperature. And that's kind of what you can look at. This is a very obvious example of that. And then for the mercury, we got this going like that. We got delta over delta T is equal to 0.0248. Now, if you've ever played with mercury, I don't recommend this. Don't ever play with mercury. But if you have and watched it flows very easily and it's very loose. It has a high surface tension but not a high viscosity. It slides over stuff really easily. So if you are going ahead and look at that and you look at delta, you'll see that delta, in order for this to work, if we have, no, actually I'm going to hold off on that because it's going to mess up my drawing. The delta T has to be much larger than delta for this one to work. So I'm actually going to go ahead and draw delta T up here, and you'll see that this is going to actually be about 50 times, delta T is going to have to be 50 times larger than delta. So I'm going to draw that down here kind of close. This is going to be delta. So you can see the switch again. The velocity through mercury, which is a very non-viscous substance, the velocity hits its final value very quickly within mercury, but mercury, even though it's a metal and fairly conductive, it's not superconductive with relation to how viscous it is. So the thermal boundary layer is going to take a little bit more time to establish itself than does the velocity boundary layer. And that's how those relations work. You can think about it, about how easily they transfer heat with relation to velocity, or you can look over this and kind of guesstimate it based on this. And since these are just sketches, nothing has to be exact. And those are the relations using Prandtl number of how the velocity, how the boundary layers change with relation to each other.